Good, then I'm sorry for all the technical difficulties. Today I'm going to talk about linear degenerate tropical flag varieties. Everything I'm talking about today is joint work in progress with Alessio Borzi from the University of Warwick. And I'm going to start about the first 5-10 minutes. I'm going to tell you what this linear degenerate part in my tropical flag varieties is supposed to mean. And then I'm going to tell a little bit about the tropical methods used to investigate these linear degenerate flag varieties. So I'm going to start by reminding you and giving some notation for what a flag variety is. So a flag of vector spaces is just a sequence of vector spaces that are all contained inside of each other. And for today, we're going to have them be contained inside of C to the n. You can do most of this theory for arbitrary vector spaces, but to get rid of some technical difficulties, we're going to restrict to C to the n today. And we're going to study sequences of vector spaces that satisfy a specific dimension requirement. So we will require the dimension of the VI to be DI for some vector D. And now the vector spaces that are contained inside of each other and that satisfy this dimension requirement can be parametrized by an algebraic variety called the flag variety. Flag variety of D and N, which is a subspace, which is a subvariety of P to the n choose D1 minus 1 cross P to the n choose Dm minus 1, where each of these vector spaces here is represented by some Plücke vector. This is where this n choose D minus 1 comes in. And this variety is cut out by some algebraic relations. So this is the variety of the Plücke relations, where the this is the variety of the Plücke relations, where the Plücke relations are the following relations. Pi, Pj plus a sum over all I that are not in I set minus j and j that are in j set minus I over their respective Plücke relations that happen if you kick out the small I from the big I and put in a small j instead. And if you do the symmetric thing on the other side, so you kick out the j and put in an I on the other side. And now to generate the flag variety from these Plücke relations, we choose sets I and j such that either the cardinality of I equals the cardinality of j, or the cardinality of I is di and the cardinality of j is di plus k, where k is in m minus I, in 1 up to m minus I. So we get a bunch of algebraic relations that generate my flag variety here. And now we are going to generalize this notion a little bit, and we're going to rewrite these well-known algebraic varieties in terms of something more combinatorial. So the idea is that we want to rewrite the flag conditions now in terms of quiver representations. Quiver is known in like Lie algebra theory when you look at directed graphs where the vertices represent vector spaces and the arrows represent linear maps. So the quiver representing a flag variety looks like this. And so on, where you have m minus 1 arrows, where m is the length of your sequence of vector spaces. And you put the identity map in between everywhere here. And now you look at subspaces ui that are embedded inside Cn, such that these restrictions are well-defined maps. And we have one additional condition that we will see throughout the talk today. Namely, we want instead of wanting the spaces to be contained inside of each other, we want the identity map restricted to UI of UI to be contained inside of UI+1. And of course, we still have this dimension requirement here as well to make this a well-defined variety. So we fix the dimension of the UI to be DI. And now if you look at this diagram, you can probably see where we're going with this, who forced us to put the identity map here. We can put other linear maps here. So maybe let's take a note. The identity, putting the identity map everywhere means that we obtain the flag variety. If we put zeros everywhere, we don't have any containment conditions. So what we get out of it is a product of Grassmannians. So we get the Grassmannian D1 n times the Grassmannian of dn n. Well, these are the dimension vectors again. And now, if you have ever thought about computing these spaces from a computational point of view, computing the flag variety is far, far, far more difficult than computing just ordinary Grassmannians, because these containment relations are relatively complicated and they induce like a lot of Plücker relations here. So what we are going, and computing the Grassmannian is very easy. Not very easy, but it's definitely far easier than computing flag varieties. So what we are interested in today is we're interested in the varieties that lie in between those two extreme cases, where we don't put the identity, but we don't put zero quite everywhere, because they kind of allow us to interpolate between this nice product of Grassmannians that is easy to compute and easy to understand, and the flag variety that is much more complicated. So we put different linear maps in between. And because for quiver representations, we allow for the GLN action on each of the vertices here, because we allow for the GLN action on each of the vertices here, we can restrict ourselves to projection maps. So projection maps, where projection map for me is it sends EI gets sent to 0 if I is in S, I is in S, and to EI otherwise. And we linearly extend this map that is defined on the bases. And these are the cases we're interested in today. These are the so-called linear degenerate flag varieties. And some people in quiver representations actually study these flag varieties, and they try to find different breakpoints, because like if you have worked with these varieties before, you know that they have different dimensions, and you can now construct precisely how many projection steps you need to break the dimension. And they study when these breaks in dimension happen and when the structure changes, when the structure is very similar to the flag variety still, and when it becomes more degenerate. And maybe one more word before we go to the tropical side. Why are these called linear degenerate flag varieties? Because if you write down the Plücker relations of these linear degenerate flag varieties, you can show that those are linear initial degenerations of the original Plücker relations. So I promised you that we are going to do something tropical today. So how do we translate this in a tropical setting? The idea to translate this in a tropical setting is to first start out with thinking about how we even translate linear spaces into a tropical setting, then how we translate flags into a tropical setting, and then how we are going to transform these maps into a tropical setting. So the tropical analogon of linear spaces are evaluated matroids. Okay. Evaluated matroids are usual matroids with evaluation function on them. So let M be a matroid of rank R. Then evaluation function is a function from N choose R to R union infinity that sends non-bases to infinity, and for bases satisfies the following rule. For all A and B in the bases of M, and all small a in big A set minus big B, there exists a small b in big B set minus A, such that the valuation of A plus the valuation of B is greater than or equal to the valuation of A set minus A union B plus the valuation of B set minus B union A. And now if you take a look at the valuation condition here and at the Plücker relations that I wrote down here, you tropicalize these Plücker relations, you can see that the tropicalization of these Plücker relations is satisfied precisely when the valuation condition is satisfied. So for the cardinality of I equal to the cardinality of J, this is precisely satisfying the Plücker relations in a tropical way. And this is a theorem that this works due to Speyer from 2008. That tells us that P is in the Dressian, which is the intersection of the tropicalization of all F in the Plücker relations, where we restrict the cardinality to just being equality. But this is equivalent to being evaluated matroid. And this is also equivalent to the tropicalization of mu being a tropical linear space. So maybe let's see on an example how this looks like, how one would cook up such a tropical linear space in practice. And for our example, we're going to look at a nice realizable tropical linear space. We're going to look at 1, 0, 0, 0. No, sorry. 1, 1, 1, 1, 0, t to the A, t to the B, 0, 1, 2, 3, 4. And now you can find the Plücker relations and the bases that correspond to this by taking the minors. So we look at which columns we have in our matrix and we compute each minor. And I computed it beforehand at some point. The valuation of 1, 2, 3 is the minimum of A and B. The valuation of 1, 3, 4 is B. The valuation of 1, 2, 4 is A. And the valuation of 2, 3, 4 is also the minimum of A and B. So what we do is we compute the determinant everywhere, and then we take the tropicalization of this determinant. And this, we can check that this actually is a valuation function on the matroid U3, 4. Sure?
Who wants to know how you define?
That's a bit more complicated. I think that's a technical detail. Like how to actually define trop mu is a technical detail I don't want to go into, except for the case where we are realizable. So in the realizable case, this is actually just the tropicalization of the linear space that is that corresponds to it. If you want to do it for evaluated matroids, you look at the circuits and the valuations of the circuits, and then you can construct a tropical linear space based on that. But the actual construction is relatively complicated. Okay, so these realizable spaces are nice in the following way as well, that we also have a different tropical object that also parameterizes them, that parameterizes just the realizable objects. And this is the tropicalization of the Grassmannian. So for the tropicalization of the Grassmannian, you take the intersection over all F that are in the Grassmannian, not just F that are pluriculations, and that gives you a different tropical space. And this is equivalent to mu being a realizable matroid, or trop mu being a realizable tropical linear space. Where realizable just means that there is some linear space that corresponds to the matroid that you can obtain the matroid from, or there is some linear space in algebraic geometry that if you take its tropicalization, it gives you this tropical linear space. Okay, so now we have dealt with the first part of these Plücker equations, and you can probably guess what happens with the second part of the Plücker equations. If we now want to describe flags of matroids, flags of linear spaces, we get analogous descriptions. So it's a theorem that is due to Haig from 12 and Brand-Jurjang from 2021. Namely, that being a point in the flag Dressian, which is just the same as the Dressian, but with all of the equations here. So the intersection over F in the Plücker relations, where I don't put a restriction on the cardinality here of their tropicalizations, is equivalent to the tropical linear spaces being contained inside of each other, the corresponding tropical linear space of the flag Dressian. And this is equivalent to the valuated matroids associated to them being a flag of valuated matroids, which is a quotient of valuated matroids. So mu I being a quotient of mu j, where being a quotient just means the same as here, as being a valuated matroid means satisfying these Plücker relations, being a quotient of valuated matroids means satisfying these additional Plücker relations. So to put it in words, for all A in the bases of Mi and B in the bases of Mi plus 1, Mj maybe, and A in A set minus B, there exists B in B set minus A, such that the valuation inequality of above is satisfied, so that val A plus val B, or we should probably specify which valuation we're taking. Here we're taking the valuation of mu I, and here we are taking the valuation of mu j. It's greater or equal to, mu I of A set minus A union B plus mu j of B set minus B union A. So now that we have some vague idea on how one could start thinking about these kinds of spaces, let's get back to our linear degenerate tropical flag variety. Let's try to see whether we can find similar conditions there. In the meantime, while I clean the board, are there any questions?
a sequence of vector spaces of that rather than one being like
exactly. Exactly. That's the idea. And the idea in the tropical setting now is basically going to be the same, where tropical projection sends things to infinity instead of to 0, right? But yeah, that's the way to. Yes, they can be the same, they can be different. Usually your set S, like usually we will have a similar variety here where you have a multi-set S, where the multi-set S tells you in which step you project away what, right? The question was whether one can think about these linear degenerate tropical, like the chains in this variety, whether one can think about them as, instead of requiring containment for all vector spaces, we require that the projection away from some set is contained inside of the other vector space. And the answer was yes, that's the way to think about it. Okay, so now let's get back to linear degenerate tropical flag varieties. Linear degenerate tropical flag varieties have actually different sets of Plucker equations that generate them. And there are some relations by Ciruli, Reli, Fang, Fourier, Fagin, and Reinecke, and some others by Lorscheid. But Alessio and I came up with even more different relations generating this linear degenerate flag variety because we like them more. And I'm just going to write them down in a tropical way. So our relations are pi tropical plus pj, tropical plus I in I set minus j union s, and j in j set minus I union s, p I set minus I union j plus p j set minus j union I. So this is going to describe the relations between two spaces, two matroids of spaces mi and mj, where I put on this map here, I put the projection with the set S here. So using these Plucker relations, we can define a linear degenerate flag Dressian with respect to all the projection sets Si, so S1 up to Sm minus 1, D and N, which is just the intersection over the tropicalization of F in these Plucker relations here. And Alessio and I showed that on the algebraic side, these Plucker relations generate the variety that we wanted to generate. And we further showed that they at least show some promise in the tropical world, because we showed that if you are a point in this linear degenerate flag Dressian, then it means that the associated tropical linear spaces are contained inside of each other. Under the appropriate projection. So PRSI of trop mu I is contained in mu I plus 1. So now we have to ask ourselves, what is the matroidal analog? Because that was the third part of the three things that are kind of shown for all the other cases. And for that, we need to find a good notion on what linear maps mean on the matroidal side of things. So we need to be able to define morphisms of evaluated matroids. So a morphism of just ordinary matroids has been known in the literature, sometimes as a strong map, sometimes as a morphism of matroids for many years, but I'm just going to give you the definition. So a morphism of matroids is a map on the ground sets satisfying the following conditions with respect to the rank function on the matroid. So that the rank of n of f of S2 minus the rank n of f of S1 is less than or equal to the rank m of S2 minus the rank m of S1 for all S1 contained inside of S2, contained inside of the ground set of the matroid at the start, so inside of M. And let me give you one short example because we're going to be talking about projections a lot today. Let me give you a projection, namely the projection 4 from U3 to U2. And to be able to define projections, you usually want to add a loop to the ground set on both sides so that you can send things to 0, essentially. So the idea is that this projection is going to do what you would expect it to do. We send 1 to 1, 2 to 2, 3 to 3, 4 to the loop. So we send 4 to 0, basically, and the loop to itself. And now we can check that this is actually a morphism of matroids by just checking the rank condition. I'm going to do it for one set. It's not that interesting to do it for all of them. So we're going to check it for the empty set in 1, 3, 4. The rank of this projection now is the rank of 1, 3 over U 2, 4 minus 0, which is 2, which is smaller than the rank of 1, 3, 4 over U 3, 4 minus the empty set, which is 0, minus the rank of the empty set, which is 0. And you can check this for all subsets here, and it works for all of them. One maybe remark about morphisms of matroids is they work pretty well for sending something from a higher rank matroid into a lower rank matroid, but they don't work at all if you want to send something from a lower rank matroid into a higher rank matroid. You can check that essentially every map that where you send something from a lower rank space into a higher rank space will not be a morphism. So the idea is now that we need to consider an equivalent cryptomorphic definition of these morphisms of matroids to be able to do such a thing for evaluated matroids. And that is the definition of an induced matroid. So instead of considering this map as this rank property, we are going to construct a new matroid from each map on ground sets. So we can define an induced matroid f to the -1 n for any map f. It doesn't need to be a morphism. And it is defined in the following way. The rank of f to the -1 n of a set S is the rank of n of f of S. And this is now a matroid over M, over the ground set M. So not over the same ground set as N, but over a different ground set. And we know that we have a morphism of matroids if and only if and only if f to the -1 of n is a quotient of m. And now we already know from the work of Brandier and Zhang and from the work of Haig that to define quotients, or that we can define quotients of evaluated matroids in the following way here, in the way that I wrote down here. So we only need to be able to define evaluation function on f to the -1n to give this definition some sense. And that is precisely what we do. And this is a kind of technical procedure because we don't just need valuations on bases, but we also need to extend our notion of valuations to that and valuations on independent sets. So we consider the map from the independent sets to R union infinity that sends I to the minimum of the bases that contain I and their valuation. So and of course, if I is not an independent set, this would just give you infinity. This function just gives you infinity. And Murata showed that this is well defined and that this is equivalent to valuation, to the valuation. So now we can define our valuation on f to the -1 in the following way. The valuation f to the -1 of nu is defined as nu bar, where nu bar is this independent set valuation. So it's usually val bar, denoted as val bar. Nu bar of f of s for any set s in M. And the proposition that we show in our paper is that this is a valuation function, and this is well defined. So now we can use our definition to investigate our tropical spaces in the setting of morphisms of evaluated matroids, because we can use this now to define morphisms of evaluated matroids by using the definition of Haig for quotients of matroids. So a map from mu, sure.
Sorry, I was not sure if I should unmute. I can't raise my hand so easily. I thought I'd just ask like this. Thanks. I have two questions about this induction. Namely, so I mean, there's this work by Bart Frank, I'm not sure. Doesn't he also introduce morphisms? Is this the same notion? That's my first question.
Can you tell me which work? I don't think I've seen
There's a PhD thesis by Bart Frank.
I've never seen it. Sorry, can't comment.
And so he I think he introduces morphisms of linear tropical linear spaces. And yes, and so the second question is, when you were talking about induction, and so when there's also this notion of induction by networks by Murata, and which gives rise to valuated matroids from valuated matroids. And I did not fully understand your definition, but I also wondered how this relates to that.
I don't think the Murata's definition of induction relates to this at all. This is, I don't think it relates. And I have never seen the PhD thesis, so I can't fully comment, but there are different notions of what a tropical linear map ought to be in literature. And we are, I don't think I will claim that we know how this relates to our definition for any of the definitions that are. But I will say I'm more familiar with the work of Mundinger, so I don't know, I'm sorry.
Okay, thanks.
Anyways, okay, so this is a morphism of evaluated matroids. If and only if f to the -1 nu defined in the way up here is a matroid quotient of mu. Yeah. So we can also now show that the usual things that you would want from a morphism of evaluated matroids are satisfied. So if I have a linear map of evaluated linear spaces, this linear map corresponds to a morphism of evaluated matroids. And if I have a morphism of evaluated matroids, it induces a morphism on the underlying matroids. Yeah. Now we can use this definition to set up our original idea in this setting. So we can now define a quiver of matroids and a quiver of matroids is a chain of morphisms. Mu I, F1, mu2, F2, and so on, mu M, where the rank of mu I is strictly smaller than the rank of mu I plus 1. This is where the fact comes in that morphisms are not really well defined for things that have increasing rank. So you need to flip around the arrows and work with morphisms in that way. And now what Alessio and I show in our paper is that this notion relates to our original linear degenerate flag varieties. So we have that projections of tropical linear spaces being contained inside one another, which is exactly what you were saying earlier, Rob, is equivalent to the associated evaluated matroids having a projection morphism in between them. So there is a PRSI from MI plus 1 to mu I is a projection morphism. Morphism of evaluated matroids, so it's a projection and a morphism of evaluated matroids. And then we have some further implications for this flag Dressian that I talked about earlier. And we have that being a point in this linear degenerate flag Dressian implies both of the things on top. So it implies that the associated tropical linear spaces are contained inside of each other under projection, and that the projection map between the associated evaluated matroids are morphisms of evaluated matroids. And for the opposite direction, we only have partial results, which is why this is still a work in progress. For the opposite direction, we have the opposite direction if all mu I are realizable. And we have the opposite direction under an additional, much stronger assumption, namely that PRSI from mu I into mu I plus 1 is also a morphism of evaluated matroids. In essence, the argument is if you have that both directions are morphisms of evaluated matroids, you have kind of a common subminor that can be extended, whose valuation can be extended to both matroids, and then everything works. So now I have some pictures of linear degenerate flag varieties. If you can share them, Dante, please. Sure. They don't work well. There are some. If you project away. Oh, sorry. The morphism, you asked whether morphisms of valuated matroids or morphisms of matroids in general don't work well for sending something from lower rank to something of higher rank. This is why this is a very, very strong condition. They work if you're projecting away enough. If your projections are very, very degenerate and the space that you're hitting with your projection has a lower rank than the matroid that you're coming from, then it works again. It just doesn't work if the image basically should have a higher rank than it's allowed to be. Yes?
What does work?
Work means there exists any kind of morphism. Like this statement makes sense, you know.
You're saying the dimension of image.
Yes.
Category is like
Exactly. And if you just put an arbitrary map from a higher rank matroid from a lower rank matroid to a higher rank matroid, the image that this is going to hit is expected to have higher dimension, which is why. Because you need, if you look at this definition, if you look at the definition in terms of the rank, you need to be able to put in S2 being the whole M. So if the image of everything is something that has higher rank than your matroid that you started out with, then nothing works anymore. That's the idea behind it. That's why this is a very strong condition, and this only works if you have pretty high projections. If the dimension if the dimensional difference here is big enough. You look okay. Sure. Okay, so here the first picture I have for you is of a tropical flag on the left side. So it's a tropical plane that contains a tropical line that contains a tropical point, which is just a point on the tropical line here. And on the left side here, I have a picture of a linear degenerate tropical flag, where this is linear degenerate with respect to 2. So if you project the point to 2, so to infinity at 2, then it will lie on the red line, even though it is not on the tropical line on this picture here. Next slide. And now maybe for a more structural point of view on these things, if you look at the flag, the associated varieties, this is how the flag Dressian of length 4 looks like. So point in line in plane in C4. It's basically parameterized by a Peterson graph with tropical line bundles over each of the graph edges plus some linearity space. And now if I degenerate, the following thing happens. We still have the structure of the Peterson graph, but instead of having a tropical line bundle over each of the edges, we have just a linear space over each of these edges. And if I degenerate one more step, then I see that I'm left with barely any structure at all. I have some tropical line with some big linearity happening over it. But that's because most of what is happening, most of the interesting things that are happening now here are going on the boundary. And if you're trying to put it into a computer algebra system, you're not going to see things that have infinity coordinates. So in these cases, if we have degeneration like for flags of length 4, at least 2, and for other flags, maybe a little bit, you can degenerate a little bit more before you start running into these issues. You should be investigating boundary components instead of the spaces themselves. So yeah, I think that was my talk. Any questions?